So today we are going to discuss from question number 11 to 15 of the 2020 physics paper. Let's see. So question number 11 is an easy question. Two identical transverse waves of frequency 300 Hz and speed 30 meters per second traveling in opposite directions along the x-axis superimpose with each other and produce a standing wave. The distance between a node and its adjacent antinode is equal to. So let's see. Two identical transverse waves. They're going to superimpose. The wavelength of a transverse wave is going to be lambda. And as they're identical, the wavelength of this one is also going to be lambda. So these two are going to superimpose. So it's going to construct this standing wave. Right. One important observation is the wavelength of the standing wave is equal to the wavelengths of the two identical transverse waves. You can see that here because I can construct the standing wave here, right? I can construct the standing wave there. So I can see the wavelength of the identical transverse waves is going to be equal to the wavelength of the standing wave. It's a very important observation. Now we know V is equal to what? F lambda. We can apply this to this transverse wave. We can apply this to this transverse wave and we can find the wavelength. What's the velocity of this standing wave? Transverse wave. What's the velocity of this transverse wave? It's going to be 30. The velocity of the transverse wave is going to be 30, which is progressive, it's going, so it's going to be a progressive transverse wave. The velocity is going to be 30. What's the frequency? 300. What's the lambda? We can find lambda, that's equal to 0.1 meters. So lambda is equal to 10 centimeters. So I can mark the nodes and the antinodes. This is going to be the node. This is another node. This is the antinode. This is another antinode. What can you say? In the antinode region, there's a lot of freedom to vibrate. Therefore, the amplitude is higher. In the node region, the freedom to vibrate is not there. So the distance between a node and the adjacent antinode is going to be this. The distance between the node and the adjacent antinode is going to be this, which is going to be lambda divided by 4, because I can break this entire length into 4 compartments. So this is going to be lambda divided by 4. So we found lambda, then we can find lambda divided by 4. So what's lambda divided by 4 going to be? 10 divided by 4. It's going to be 2.5 centimeters. I hope you understood this. Right, now we have to do the next question. 12th one. Very long 8 parallel wires, each carrying a current of 10 amperes. The directions of the current in each wire as shown in the figure. The magnitude and the direction of the magnetic flux density produced at the center C. So I'll just remind you the theory first before discussing the question, because it doesn't take time for the theory. So these theory parts are very easy, so you have to get marks on these easy topics. Right, let's see. If I have a current carrying wire like this, carrying current I, and suppose I need to find the magnetic field intensity at a point A at a distance R. So at a distance of R, at a point A, I have to find the magnetic field intensity. How can I do that? I have this equation. Magnetic field intensity at A is equal to mu divided by 245, 2 divided by 45 times 2I divided by R. Or you can write it like mu I divided by 2R, 25R. So BA is equal to mu divided by 45 times 2I divided by R. I can also write it as mu I divided by 25R. Now, if you keep your thumb like this, and also if you curl your fingers like this, and hold my thumb in the direction of the movement of current. So I hold my thumb in the direction of the movement of current. If current goes up, I have to hold the thumb up like this. And I have to curl my fingers in the direction of the magnetic field intensity. And you can see this. So the fingers are curled in the direction of the magnetic field intensity. So it's a representation. Right. this. What do you mean by mu here? That's actually magnetic permeability. If you consider vacuum, it's going to be mu naught. If you consider vacuum, mu, which is the magnetic permeability, becomes the magnetic permeability in free space or vacuum. Right. Now, having understood this, we can come to the question. So we have very long 8 parallel wires. I think you can see the diagram. Now to think of it. So I have these cross marks here, which represent the directions of the currents. Right. So these are center C, and these are the directions of the currents. Right, what can you say? The gap here is 10 centimeters. The gap here is also 10 centimeters. The gap here is 10 centimeters. And the gap here is also 10 centimeters. So we've marked all the information that's necessary for solving the question. Right, look at this. Right, we're going to do something now. I said we had to hold the thumb in the direction of the movement of current. Can you see current is coming out of the board? If the current is coming out of the board, I have to hold my thumb like this. So if I curl my fingers, the fingers show the direction of the magnetic field intensity. So if the current is coming out like this, the magnetic field exists like this, in this direction. Look at this one. My thumb is coming out because the current is coming out. Fingers curl in the direction of the magnetic field intensity at this point. So the direction is going to be the opposite direction. And you know the magnitudes are going to be equal because the currents that are carried are equal. They mentioned that the currents that are carried are equal, which is 10 amperes each. Currents are equal, the distances are equal. From here to here, the distance is equal from the distance from here to here. The distances are equal, the currents are equal. You know, magnetic field intensity means mu I divided by 2 phi r. So if the current is the same and the distance is the same to that point, then the magnetic field intensities produced are the same in terms of magnitude. But here the directions are different, right? So this one cancels off this one. Then can you see when I have two identical directions of the movement of current and the same distances to that point, the effect of these two wires is not there to create a magnetic field intensity here. So what should you understand at the end? There is no resultant magnetic field intensity at C due to two identical current carrying wires at equal distances from that point. I think you can understand what I'm saying. So then we can identify that there's no effect from this and this. Similarly, the same logic is valid for these two. You logic it out. The same logic is valid for these two as well, because they're going the same direction and they're placed at the same distance from the center. Then the resultant magnetic field intensity is caused due to current carrying wires that are allowing current to flow in opposite directions, right? I think you understood this. Now the question becomes simplified and easy. So let's see. So now the question becomes simplified. So now I have the point C, and then at distance of 10 centimeters from here and 10 centimeters from here, I have this current here and this current here. So the current values of the currents are going to be 10 amperes each. So this 10 centimeters, right? This current carrying wire is pushing the current towards the board. Then the magnetic field intensity is going down like this. This current carrying wire is taking the current out of the board, which means it produces the magnetic field intensity down. and they're acting in the same direction, which means you have to add up the magnetic field intensities at that point due to each of the wires. Right. So let's see one wire. If we can find the magnetic field intensity caused due to one wire and multiply it by 2, we can find the resultant magnetic field intensity. It's very easy, right? Let's look at this. So we know magnetic field intensity B is equal to mu divided by 4 phi times 2I divided by R. Right. So let's calculate the magnetic field intensity. They have given the value of mu divided by 4 phi to be 10 to the power minus 7. Right. And then you have to multiply this by 2. And what's the current? 10 amperes. What's the distance? Now we have to mention everything in standard units. So the distance is going to be 0.1 meters. 0.1 meters. And now this is due to one current carrying wire. So to multiply this by 2 definitely to have the resultant magnetic field intensity at point C, which is the center. So to multiply this by 2. So simplifying, I can say this 100, so this becomes 10 to the power minus 5. So I get 4 times 10 to the power minus 5. 4 times 10 to the power minus 5 Teslas, which provides the magnetic field intensity. I can convert this into, I can say this is 4 times 10 times 10 to the power minus 5 times 10. You know math, right? So I can write 4 times 10 to the power minus 6. This is equal to 4 times 10 to the power minus 5. So what is 10 to the power minus 6? Micro. So I can say B is equal to what? 40 microteslas. I hope you understood this. Right. Come to the 13th question, which is a question from humidity. Two adjacent rooms A and B at same temperature, connected by a closed door, are initially at relative humidity 60% and 90%, respectively. The volume of room A is twice that of room B. If the door is open for a long time at the same temperature, very important, same temperature, you have to highlight these points. What would be the final relative humidity of the rooms? So let's see. Physics is such a beautiful subject. It's one of the easiest subjects if you can really understand the theory. So once you understand the theory, you can solve any question. Because if you really understand the substance of the theory, application of that theory is what you should do for a question. So just take some time. Don't just think it's a waste of time thinking. No, you can go out a bit, you can take some rest, right? You can get out of the house and just walk a little in the road and just think about the questions. Like suppose you not get an answer for a question, just contemplate over that question, think about that question. So don't worry. So once you spend a lot of time with physics, physics will become easy for you. So you have to love physics for physics to be comfortable. And also remember, I'm always saying in classes, what I'm saying is future is the constructive present. So what you do now is going to affect your future. So now when you're crossing a road, you've got to cross the road with utmost care. You have to be aware that vehicles are coming from both sides. So when you're crossing the road, you have to be alert, attentive when you're crossing the road. Just like that, now you're faced with an exam. So you have to work for the exam. Don't do anything that shies away from the exam. Everything that you do now should be done. Everything that you should do now is to be done for the exam. You should do everything for the exam. Don't postpone things. And even if you find half an hour to study, please study during that half an hour. You can enjoy too, you listen to some music, but at the same time, you have to give a lot of attention on finishing this properly. Right. So we have the 13th question. Two adjacent rooms A and B at same temperature. So look at this. So room A and room B. Right? So room A has a relative humidity of 60% and its volume is 2V at the same temperature T. Room B has a relative humidity of 90%, but the volume is V. The amount of vapor per unit volume in room A and B at saturated state is going to be the same. Can you understand that? When, suppose room A and room B are saturated, if room A and room B are saturated, when you consider saturated instant, then we can say the mass per unit volume or the absolute humidity at saturation, mass per unit volume, is going to be the same because the temperatures are the same. Temperatures are the same, but their volumes are different. That means the overall mass in B and the overall mass in A at saturated state is going to be different. But the mass per unit volume is going to be the same. Is that clear? So if the mass, right, per unit volume is the same, right? What can you say the mass is for saturated state at A? When you consider a room A which is saturated, which has a volume of 2V, I can say the mass is going to be 2 ms. And the mass at saturation in room B should be ms. Because the volume here is V and the volume here is 2V. So there should be twice this to saturate room A at the same temperature. Just try to understand this. So room B has a mass of ms to saturate it. Room A has a mass of 2 ms to saturate it. Because I have twice the space to saturate, then I need twice the amount of mass. But remember, the mass per unit volume is going to be the same, right? I hope you understood this. So the mass that I need to saturate room B is going to be ms. The mass that I need to saturate room A is going to be 2 ms. Hope it's clear. Right. Now you know relative humidity is equal to M divided by ms times 100%. Let's apply this for room A. The relative humidity of room A is 60%. The mass, I don't know, because it's not saturated yet, 60%. And the saturated mass is going to be 2 ms. The mass that I need to saturate room A is going to be 2 ms. So I should multiply this by 100%. Then I get the mass that's available in room A. Mass in room A is going to be equal to, so 60 divided by 100 is 0.6. That multiplied by 2 becomes 1.2. So I get 1.2 ms. If I consider room B, what can I say? If I consider room B, again I can apply the equation where humidity is equal to mass divided by mass available divided by mass to saturate that room times 100%. What's the mass that's available? Yeah, it's going to be, we have to find it out. So relative humidity of this room B is going to be 90%. Mass available is MB. And mass to saturate is going to be ms. So I multiply this by 100%. So I get mass available at B, MB is equal to 90 divided by 100, which is going to be 0.9 ms. I hope you understood this. Right. Now, when I open these two rooms, so I'm going to erase this now. We have MA to be 1.2, MB to be 0.9 ms. Right? So once you open these two rooms, what's going to happen? The vapor is going to mix. The vapor is going to mix. So you can pause the video or you can take screenshots and save these things. So you can pause the video and copy the notes, whatever that's necessary. Right? So in this room that's open now, the total mass is going to be MA plus MB. What's MA plus MB equal to? 0.9 ms plus 1.2 ms, which gives you 2.1 ms. I hope you understood this. What's the total volume? 3V. If the total volume is 3V, the mass that I need to saturate this total volume at the temperature T is going to be equal to 3 ms, right? Because the mass that I needed to saturate a room of volume V was how much? ms. 2V was how much? 2 ms. Then 3V should be how much? 3 ms. Then I can apply the equation where humidity is equal to mass available in this entire space divided by the mass that I should need to saturate this space, ms times 100%. What's the mass that's available? 2.1 ms. What's the mass that I need to saturate this space with? 3 ms. So this should be multiplied by 100%. So I get what? 210 divided by 3. 210 divided by 3 is 70%. So the answer is going to be 70%. So the relative humidity in this space is going to be 70%. A very easy question. I hope you understood this. Right. And you can actually solve this question mentally. Look at this. How can you solve this question mentally? Okay, now picture this in your imagination together, now with me, together, right? So we have room A and we have room B. Room A has a relative humidity of how much? 60%. Room B has a relative humidity of how much? 90%. The volume of room A is going to be how much? 2V. What's the volume of room B? V. So you know the mass that I need to saturate room A is going to be 2 ms. The mass that I need to saturate room B is going to be ms. So what's the relative humidity equal to? The mass that's available divided by what? Mass that I need to saturate times 100%. So mass available is going to be equal to what? Look at the equation mentally. Relative humidity is equal to m divided by ms times 100%. Then I get what? For room A, 60 is equal to what? Ma divided by what? 2 ms times what? 100%. Then 60 divided by 100, we can see mentally is going to be 0.6. So 0.6 multiplied by 2 gives you what? 1.2 ms. So 1.2 ms, you can count it out like that. And then for room B, 90 is equal to what? Ma divided by what? Ms times 100%. So you can take 90 divided by 100, it's 0.9. So 0.9 times ms is going to be mb. So you get 1.2 ms for room A, 0.9 ms as available mass in what? Room B. Then the total mass is going to be 2.1 ms. And you know, if you have the total volume of 3V at the end, but divide what? The available mass, that is 2.1 ms, but the mass to saturate is going to be 3 ms. And then you have to multiply this by 100%, so you get 70%. See, you can solve this question mentally, not write these equations physically. So I'm teaching these things. These are very critical advices to do the paper very fast, because there's no point taking a long time for a question, because you are cramping for time. And last time the students wrote, and they're telling that they didn't have time. They were able to solve questions. They felt like they could solve the questions, but they came up with these problems that, well, they did not have time, though they were able to solve the question. That's because they don't have enough practice. And also, you have to come up with the shortcuts. You've got to do some questions mentally too. Right. So we have question number 14 now. Let's see. So we have all batteries shown in the figure having negligible internal resistances. If the capacity C is ideal, what is the potential difference across C? Let's see. What can you say? So here I have 2V, resistance 3 ohms, 3V, C, right, and here 6 volts, 5 ohms, right, it's clear. Alright, look at this. So all the batteries shown in the circuit have negligible internal resistances. If the capacitor C is ideal, what is the potential difference across C? Look at this. I can use this grounding technique. I can say the potential difference. Okay, let's start again. I can use this grounding technique. I can earth any point I like. So I'm going to earth this point. Right? I can earth any point I like. So for example, I'm going to earth this point. Is that clear? So when I earth this point, the potential is going to be 0. Now we know the potential difference across this is going to be 3 volts. But listen, if you consider a capacitor like this at steady state, when the capacitor is at steady state, which means there's no current flow. So when the capacitor is at steady state, there's no current flowing through it. Once it has been charged, there's no current flow. Right? So here, if the potential here is 0, can you understand, is everybody clear that the potential here should be plus 3? Because the potential difference will be 3 volts for the battery. Then I should, if I have 0 here, I should have plus 3 here. This plus 3 here, same wire, plus 3 here, plus 3 here. It is 2 volts. If I am to have 2 volts here, I should have plus 1 volts here, because the potential difference is 2 volts. Then plus 3 minus 1 gives you 2. Now you know, how can you find the potential here? If you can find the potential here, you know the potential here, and you know the potential here. If I can find the potential here, I can find the potential difference across the capacitor. But the goal is to find the potential here. How can you do that? Well, you can apply Kirchhoff's. Now you know current doesn't flow through this. It doesn't flow through the capacitor. So the current follows a path like this. It's the other way around, because here the voltage is higher. So the current flows like this. Right, let's call the current I, right? Okay, let's find the current. Now you know sigma E is equal to what? Sigma AR. That's how we can find the current, right? So I can apply to this entire circuit in this direction. Sigma E is equal to what? Sigma IR. What's sigma E? So I have 6 volts in this direction, 2 volts in this direction, 6 volts in this direction, 6 volts in this direction, 2 volts in this direction. So 6 volts is trying to send the current in this direction, 2 volts is trying to send the current in that direction. So it's like clockwise here and anti-clockwise there. Then 6 minus 2 gives you sigma E, because they're in opposite directions. Alright, and, right, what can I say? Sigma IR, right? So when you go like this, I have the current I. The current is I. So current I times 3 plus, when I go like this, current I times 5. So you get 4 is equal to what? 8I. So the current is equal to what? 0.5 amperes. Is that clear? So the current here is going to be 0.5 amperes. Right. So you found the current. If you know the current now, when current is flowing through this resistor, there's going to be a potential drop. Right? There's a potential difference across these 3 ohms, and there's going to be a potential drop now. So I had 1 here, and a current of 0.5 goes across 3 ohms. You know V equals IR. Then if the current is half, resistance is 3, I get the potential difference across the resistor to be 1.5 volts. So you know the potential drop is going to be 1.5 volts. So from 1, I should subtract 1.5 volts. So what happens then? If I subtract, because there's going to be potential drop, because current is going in this direction. Current flows in the direction of dropping the voltage. Right? So what happens then? I have 1 minus 1.5 volts. Right? So 1 minus 1.5 volts. Or you can take like this. Alright? So I can take this as point A, this as point B. So VA minus VB is equal to what? Potential difference of 1.5. So what is VA? 1. So 1 minus VB is equal to 1.5. Right? So VB should be equal to what? 1 minus 1.5, which is minus 0.5. That's clear? So the potential at B is equal to what? Minus 0.5 volts. Then I should get minus 0.5 volts here as well. Is that clear? So I should get minus 0.5 volts here as well. So what's the potential difference across the capacitor? 0 minus 0.5 volts. So what's the answer? Plus 0.5 volts is going to be the potential difference across the capacitor. I hope you understood this. Right. For the next question, which of the following statements is incorrect? Now I'm not going to explain this entire thing because it's highly theory based. It's actually like if you can read the note about this electronic part, which is field effect transistors, you can easily understand this because questions are coming from the theory note exactly. Right, so I just give you the answer, which of the following is incorrect. The answer is the 5th one. When an op-amp is used as a voltage comparator, closed loop state is used. No, it's the open loop state is used. All our statements are correct, but here in the 5th statement should be the open loop. I just remind that 5th statement quickly. Right, what do you mean by that? Open loop state and not the closed loop. Voltage comparator. We can compare voltages. which is high, which is low. So if I have this op amp, this is the positive terminal, this is the negative terminal, right? And here, right, I have V0. Look at this. I can take this as V1 and this as V2. The input here, V1, input here, V2. This is the non-inverting terminal, this is the inverting terminal, right? So if I say V plus minus V minus, right? V plus minus V minus is going to be the difference between the inputs, V plus minus V minus. This is actually amplified to give you the output. Suppose V1 is greater than V2, what's going to happen? If V1 is greater than V2, what's going to happen? The input is amplified. So if V1 is greater than V2, which means you get a positive one. So there's a positive amplification. You can see that. If V2 is greater than V1, what's going to happen? You get a negative signal. That's how you can compare voltages. So I hope you understood this. Let's meet in the next video.